Today we're going to do another lab simulation, this time trying to find a relationship between gravitational force and distance that separates the two objects. And from that, we're going to actually determine the value of Newton's universal constant, that 6.67 times 10 to the minus 11 number that we've used quite a few times through gravity force in gravitational fields. And this is going to be a lab simulation, so you're going to go to your Google Classroom, you're going to click on the link that's provided at the bottom, Gravity Force Lab, and it's going to take you to a page that looks something like this. Let's make this a little bit bigger so we can see it better. You can make this whatever size you want, maximize it if you want. You're going to click on play here, and it's going to take you to a page that looks like this. Now we can see we have two masses here, mass 1, mass 2, beside each other, a certain distance apart. Two masses that are labeled here, 100 kilograms and 400 kilograms. The first thing that I want you to do when you do this is change those masses. I don't want you to use 100 and 400. The reason for that is simple. I don't want any two people in this room to have the same data. So that means that if you use 100 and 400 kilograms, if everybody's using those two masses, then we run the chance of people having the same data. If you change yours to 150 and 410, good enough. If you change it to 90 and I don't care what they are, okay? Change them to something. So I'm going to go, I didn't know it did that. 108 kilograms and 390 kilograms, good with that, okay? Just change them from what the default values are. Now, you can see these masses. When I change these masses, it changed the forces on the top as well. You can see the force on mass 2 by mass 1, 0.000000175. Mass force on the other one's exactly the same, right? Go figure. If object A applies a force on object B applies an equal and opposite force on object A. What you're going to do from one trial to the next is change that distance. We're going to measure the distance here. Okay, measure the distance. This would be 4 meters. Now you're going to change that distance. So let's change the distance to whatever you want. Move the other one if you want. I don't care which one you move. Move them both. Measure the new distance. So for every trial, from one trial to the next, you're going to increase or decrease the distance, the separation distance, and then you're going to see how the force responds to that. See what the force becomes as a result of that. I move that again. You can see that the force changed there. The distance changed, force changed. Now what you're going to do is record both of those values. The separation distance, the distance that we measured with the ruler there, and the gravitational force that resulted from that. Make sure you put your units in there. Some of you, the last time we did a simulation, and I did not include the units for you, some of you also didn't include the units. You need to include the units for this, right? And you also need to record the values of your masses. Even though those aren't changing, you need to record the values of the masses. These are your control variables, right? Now, the important control variables, mass 1 and mass 2. Your separation distance would be your manipulated variable, and your gravity force would be your responding variable. I want you to do this 10 times, at least 10 times. You're not changing the mass, staying the same from one trial to the next, but you're going to change the distance 10 times and the corresponding force 10 times. Now, last time you did a lab, had it in last week, got it back over the weekend, you had to find some relationships. The relationships are either linear, quadratic, inverse, or inverse square. What you're going to do first in your analysis is plot a graph of force versus distance, force versus separation distance. You know, I'm not going to show you the shape of that graph, what the shape of that graph is going to be, but you are going to plot it, and you're going to plot a trend line. Not a random trend line, a trend line that fits the curve. I'll give you a little hint. This will not be a straight line. Don't plot a linear trend line, because that's wrong. Plot a trend line that matches the curve. Just keep trying until you find one that matches the curve really well. You do not need to display the equation for this one. Got it? You do not need to display the equation for this one. Now, so what you're going to do, guys, is draw the graph and then identify what relationship that is. Is it linear? Is it whatever? And then, then you're going to do something else. You're going to calculate the inverse of the separation distance squared. In other words, 1 over r squared. So whatever your value of r is, let's say your value of r was 2 meters, square it. That's 4. And then 1 over 4 is 0.25. Does that make sense? So square the distance and then flip it over. Make sure you include the units for this as well. The gravitational force isn't going to change. It's the same as the second column was in your first table, right? It's just your first column is going to change. It's not r anymore. It's 1 over r squared. And then you're going to plot a new graph of force versus 1 over r squared. Watch the units there again, especially for the 1 over r squared. Those are tricky. Then you're going to plot a graph. And this one is going to be a straight line. So for this one, it should look like this. And it should look at really well because it's nice cooked up data from the simulation. It should give us a nice straight line. Make sure you do include a trend line. And this time, make sure you do include the equation. Now, from this equation and this trend line, we are going to determine the value of G. We're going to determine the value of the gravitational constant. Here's how we're going to do it. We've talked about this once or twice before, this technique. This is more of a physics 30 technique. We're just kind of introducing it to you here. In order to figure out what G is, we have to figure out what the slope of this graph represents. What is the slope of the graph? Is it G? No, it's not. Now, if I had to guess what the slope of this graph represents, I would probably have maybe a 10% chance of guessing correct. I have to do an analysis here. So here's our analysis. We're going to come up with an equation from the graph, and you're going to need to show this analysis, by the way, and come up with an equation from class. From the graph, what equation would describe this graph? What's the general equation that describes any straight line graph? Any straight line graph, guys, any straight line graph. What is it? Nope. There's no square in it. Any straight line graph, y equals? Yeah, y equals mx plus b. Now, b stands for the y-intercept, and it will be 0 in this, or really, really close to 0, so we can just cross that off, okay? So my equation becomes y equals mx. On my y-axis is the force. M stands for what? Come on, you math whizzes here. Slope, and there's a slope of the graph, good. And x, my x-axis is 1 over r squared. So you're doing this for the second graph, not for the first graph, okay? F versus r, I don't want to do anything with that. F versus 1 over r squared, that's what I want to do. Now, what equation have we done in class that has f and r squared on the bottom? What equation have we used in class that has both f and r squared in the context of gravitational force? Come on, easiest question ever. What equation have we done in class? Look at your data sheet. What equation have we done in class with f and r squared? Avery? Yep. Good. F is equal to g m1 m2 over r squared. Now, here's what I want you to do. Take another color, cross it off. Cross off f because it's in both. Cross off r squared because it's in both. What are we left with? Well, we're left with the slope in this one. What are we left with over here? gm1, m2. So what's the slope of this graph? G times m1 times m2. Who would have predicted that, right? If we had to guess what the slope represented, I don't know about you, but I wouldn't have predicted it's equal to G times m1 times m2. Remember what we're trying to find? Trying to find the value of G. Well, Google Sheets will give me the value of the slope. M1 Well, we measured that. That's the first thing we did, right, is measure the value of mass. In M2, we measure the value of mass 2 as well. The only thing we don't have here is G. That's what we're trying to find, is the gravitational constant here. So just rearrange that, solve for the gravitational constant. Should be really close to 6.67 times 10 to the minus 11, right? If you get an exponent that's off, not 10 to the minus 11, probably means you did a unit conversion somewhere wrong, whatever. You get a number that's way off of 6.67, might be off a little bit, that's okay. But if it's way off, because this is computer generated data, like you've made a mistake somewhere. It should be very close to 6.67 times 10 to the minus 11. That's it. That's all we got to do for this one. So you're not writing up a procedure for this. You don't even need to identify variables for this one. You're not doing a conclusion for this one. It's just what you see is what you get there.